time in Kangra, and I have been to Dharamsala many times, but from Palampur to here, this is the first time. And I don't understand the meaning of the keynote speaker, in fact, because in the different conferences where I have attended, everybody is given a particular time and everybody speaks. Yes, there is a culture of an evening talk as well, but for this particular talk, I thought of discussing next generation quantum engineering or next generation quantum technology. Is everybody here able to see? Alright. So when it comes to the next generation quantum engineering, then obviously the first question will come, what is first generation quantum engineering? And even before that, what is quantum science? So all these questions are already. So I will just go through with a little bit history of the evolution of the quantum science and how this development the quantum sciences are affecting our day-to-day life. So that's my objective. So you look at this timeline up here from 1900 to until now that I have plotted. So very first idea of this quantum came up, it was given by the Planck. It was in 1900. So in the 1900, there was a mystery that how the radiation coming from a black body, how does it behave? So Planck gave an idea. Alright. So that came up in 1900. So first time he considered the energy as a bundle of the quanta. So energy is not a continuous form, but it has a small bundle, the quanta. So that's the first time the bird he proposed energy as a quanta. And then in 1905, Einstein gave a beautiful explanation that when we shine light onto some material, then the electrons comes out. So there was some mystery that how these things are happening. And Einstein, considering the concept of the Planck, then he explained the photoelectric effect. So that came up in 1905. That's another thing, and we use it in our life, daily life, we use it. And there are multiple things happen. In 1930, the Bohr gave an idea that there is a nucleus and the electrons around the nucleus, they don't take any other position, but they revolve in a particular orbits. So there also these orbits have a different energy. So energy was again quantized. That thing came up. But the real new mechanics or new physics came up, developed in 1925, where the Schrödinger, Dirac, Heisenberg, they gave a new theory to explain the motion of the particle at the atomic level. So that is the Schrödinger equation, and this came in 1925. So consider from 1925 to until now, 100 years have been passed, right? A lot of things are happening, and then the new statistics came up. So you see a name of person called Bose. So Bose was our Satyendra Bose. His name is there, so that Bose-Einstein statistics. One type of the particle, atomic particle, they are named as a bosons only, named after our Indian scientist. And there are multiple development. Then the Bloch theory came up, and it described the behavior of the, especially semiconductors, right? And also many solid state materials that came up, because materials are the backbone for any development. You have to do something, ultimately start with the material. Okay. And starting in this times, 1947, once the band theory came up, people started working with the semiconductor material, they started making transistor. So earlier the transistor, the semiconductor used to be, those transistor, the diode used to be quite big in a vacuum tube diode and transistor. But nowadays those are very tiny, so much tiny that we cannot see. So that was a discovery in the 1947, the transistor came up. And in 1964, these three people, Bardi, Bentley and Shockley, they made first solid state transistor. So think of it, in 1964, first time the solid state transistor was made. And after that, so many chips were made. Now we see these computers, and there's big processors having multiple transistors in it. Millions of the transistors in 1 inch square area, 1 inch square area. So a lot of these developments were happening. So I will see this area that what is in this region. This is the basic foundation of current day's technology. And what are the few? I have few examples that what technology that we are using based on these principles. So that I will say what is the application of this technology. Once we done this, then we'll go for the next generation of the quantum technology. This everybody understands. This is our periodic table, where the Mandi arranges all different elements in particular order, and based on their properties, chemical and physical, chemical properties based on that, and how one particular elements have a different property than another property, and why we classify from one to another. Though Mandi did it just by his observation, but in order to understand why the things are happening, then we need to know what is happening through the quantum mechanics. Understanding the quantum mechanics help us in explaining this. Nowadays we use X-rays for the multiple purposes. Right? So if you use different type of the X-rays, I think I invited him. So X-rays can be used depending on their energy in the different range and for various purposes. As for security purposes also you can use it. You can use it to see how different atoms are arranged inside a solid. This dice is, I think, obstructing you people. Right? I don't know. Can we move? Fine. So this is another application of the quantum science in order to see that why the things are happening at this level. We use solar cells. Now there is a lot of focus. Government's focus is to use that. We use the solar cells, solar cell battery, and so that we can save a lot of energy. And not only that, if we make it, we can produce more solar energy. Not only we can use it for our own purpose, and also we can put it into the grid. It can be utilized. Another thing that you see is here is the LED. That's a light emitting diode. So again, I say that it's a diode, and this diode can also emit light. And nowadays we all are using this. In my time when I was young, we used to have this tungsten filament bulb. So 100 watt of the bulb or 200 watt of the bulb. So it means 100 watt of the bulb. So it is taking so much energy. So it runs for the 10 hours, it will take 1 unit of the energy. Nowadays we use LED. And what is of the LED? 9 watt, 11 watt. So for the same unit of the energy, you can have a light for 100 hours. Right? So there is a lot of energy saving in this sense. This all happened based on the concept of the quantum mechanics. Right? Those are the basic concepts. And I feel this, if somebody can move it, because somehow they say that these people cannot see. So these are the applications happening. Right? Coming out to the next some applications. In order to understand why, say, we all are wearing different type of the clothes. And if I see it appear this wall is white, this is of some brown color, I am wearing black, blue. Why something is having a particular type of the color? You can't understand it without quantum mechanics. Right? This is a phenomenon of fluorescence and phosphorescence. You shine a light on a material, the material reflects the light in other sense. Phosphorescence, you shine a light now, material reflect the light after some time. So in order to understand all that, we need quantum mechanics. Laser, that we use it. So I am using this laser pointer here. Right? How this laser works. This is a very soft, low energy laser. But one can have a laser of very high intense energy. India is building a petawatt laser in Hyderabad. So huge facilities coming up. So laser, we can understand only if we understand this much quantum mechanics. And these are some other applications. Here is the written MRI, magnetic resonance imaging. We use it. Doctor nowadays very often they prescribe that go for the MRI. And we do it. And what we can do, we can see the image of our organs here. If there is some fracture in the body, so that can also be seen. What is happening inside the brain, that all can be seen with the MRI. And there's a lot of physics behind this. We say 1.5 Tesla MRI or 3 Tesla MRI. It has some meaning. If you understand magnetic field, so that magnetic field unit is a Tesla. There's a magnetic field we use there for this. When we go to the laboratory, like from our naked eye, how small can we see? Like in our normal purpose, our hair thickness is 20 to 80 micron. This much thickness we can see. If we go to 1 micron, the size of the bacteria, we cannot see our naked eye. But we have a curiosity to see even at lower and lower scale. So we have the scanning electron microscope. Here, the property of the electron that we consider as a particle, when we make a microscope, we use the property that electron behave as a wave also. So we use this property to see the objects. And this is all. And now coming on to the scanning tunnel microscope, using this technique, we can see the individual atoms as well. But you see up here, these are the different atoms as in a particular order. And nowadays in the science, these things are done very routinely. Right? So as I see that there are many developments are happening. So in my phone, I'm in my pocket, I have a phone. It's a very powerful computer. This is a very powerful computer. Without these, we cannot think of our life these times. This all have come because of the development of the science. Now one more example that I take. You see this GPS. In all our mobile phones, we have this global positioning system, GPS system. And how the GPS is working. So much intricate technology is happening here. So we are somewhere, this GPS is in our phone is in our pocket, and this is sending the signal to satellites. And what are these satellites? They are revolving around our Earth all the time. So there are at least 24 satellites revolving around the Earth all the time, especially for this purpose. So in fact, American Navy, that is having control of all these satellites and using these and at any time in order to locate your position, we need a signal from 3 satellites, not from 1. One satellite tells one thing, another thing, and if you take the data from the 3 only, then you can say with the right precision that you are located in this position. So this is just with the satellite you do it. And not only this, you have heard of that Einstein, he was a great scientist. He gave a theory of special theory of relativity in 1905, and later on he developed the general theory of relativity. So general theory of relativity is very complex mathematics. Special theory of relativity is easy to understand, but unless we use those principles, we cannot locate our position. So every day we are using the concept of the Einstein in our phone whenever we are walking and we are passing. So these are the very important things done by our forefathers, right? They were there, and it is not done by one person only. Somebody conceived an idea, another person thought over it, they added something on it, and until over a period we come on to at this particular stage. So science is a very slow development process. Okay, now I come on to my second part, and there are many more examples for that. Can somebody what is this? Someone will press. Okay. Quantum technology. Recently, Indian government, they have promised 6,000 crore rupees to be invested in over a period of 7 years to invest in the quantum technology. And it is said in the coming time, whoever will be having this control over second generation of quantum technology, whoever will be able to make a quantum computer or will be good in quantum communication, they will rule the world. So now I go back to my same diagram. Right? So what we have done. So in the second generation of the quantum technology, quantum is what we will do, that we now control the individual quantum entity. Earlier we were having some material, and how those materials are behaving, we use those properties for our purpose. We made a transistor in our material, and we play this transistor with another transistor and make different combination, and we made a computer. Now, forget about the transistor. Now we go to control the individual atoms. How individual atoms are behaving and how individual photons are behaving. If we can harness their properties for making some new technology, that is our second generation. So, even before that, like this, I said, it's a down to the classical computer. So once somebody made the transistor, and slowly by 1975, people have an idea how to make a computer, and those ideas came out. And if, in fact, whatever the chips you are seeing is fourth generation, there you are reducing the size of those chips. Earlier, the computer used to be very huge. Maybe the first computer will require this whole room to fit in. And the memory for that was only 1 or 2 megabyte only. Right? Very small memory. And nowadays, even a very high memory stuff can be. We have 1 TB hard disk in our computer. So that's all developments are happening. And idea of the neural network came up. This first started in 1948 around or 49 around. Somebody came. Then they thought of computer. Now they say we should make a computer which work on the principle that how our brain is behaving. So they took some analogy from the functioning of the brain. No doubt we still don't understand how the brain functions, but still, whatever the understanding they have, they use the idea of neural network. And these days, nowadays, this is very much in use. These two guys, John Hopfield and Jeffrey Hinton, so they gave another theory. They gave the foundational neural network theories, Hopfield and Hinton, and this was done around 1986. And these guys were awarded Nobel Prize. So artificial intelligence that you see, nowadays this is based on their ideas. Okay. So these are new things happening in the field. Okay. And we have already made computer by this time. So come to 2000, we already have a computer. We have a lot of understanding of computer. Now we go for quantum computer. If we go for quantum computer, we need to have new circuitry. So the quantum circuits and error correction in the first qubits, those ideas were given some after 1990s. And nowadays, when you see here, we say this is now second evolution of the quantum engineering. This is what we see now, and this is now again down of the new artificial intelligence, new ways of artificial intelligence. We are somewhere here, and if we can push the things further, we will have much better and more efficient technology. So some of them that I will discuss. When we say next generation quantum engineering, what are the main different main things comes up here is quantum computer that everybody hears. Right? There is something called quantum communication. There is another word that you see, quantum sensing and metrology. So all these three are different things. No doubt in India, all these things are in very early stage, but after the government's push, things are moving much faster. Scientists are thinking in this direction. And all these things are based on some basic concepts. Quantum computer, you have in our classical computer 0 and 1 state of the transistor. Those things we call bit. For quantum computer, we call those as a quantum bit. So we have to make the quantum bits. We need to have some material, not the transistor now, some material which can be made as a quantum bit. We need to understand what is quantum entanglement and what is EPR paradox. So I will discuss a little bit of this. And this word is very much known, quantum teleportation. So in sci-fi movie, you will see that person is somewhere here and they went into a machine and suddenly they reach to another. So this is a very fascinating idea that one can transmit one person to another place. But in reality, it does not happen that way. And so I will say that what can be achieved here. Some sort of teleportation is achieved. Okay, so all these things are part of the second generation of the quantum technology. Let me go to this first quantum methodology. I hope. So this is the atomic clock. We use clock every other, right? So how do we work with the clock? So very first clock that we see, we have a pendulum, which is moving, and how much time it is taking for one oscillation, and that we convert into clock time. In our watches, we also go for the time. There is some quartz crystal. The quartz crystals, they have a very high frequency of their vibrations. You can count those vibrations and say how much, if a crystal has done say 10,000 vibrations, this corresponds to this much time. That gives more precise time. In an atomic clock, we don't see both the thing. We say in one particular atom, how much is their vibrational frequency. If you look at the definition of the second, right? So the cesium atom, it vibrates for I think 91 billion times. I know the figure in Hindi. I remember during my school days. So it takes 9 arab 19 crore 26 lakh 31,770 per second. Right? So these many times, if a cesium atom it has this much vibration, that is considered a 1 second. So to harness the property of those atomic vibration, one can make atomic clock. Nowadays the clocks are already there. When we go to the GPS system, we use those atomic clocks. And there is a lot of research is going on. And this photograph up here from a lab in IIT Mandi, this group is working on atomic clock. So they will be used this property for most sensitive time measurement. Then the next you see, now we are now thinking at the atomic level. Suppose we have to understand how much is a small force and a small displacement. Some of you might have seen, might have known a word, atomic force microscope. So in order to image something, image the surface of some substance, we use AFM, atomic force microscope. From our eyes that we see, okay, this is skin is very much flat, right? Or even floor is very much flat. But if you look at the atomic level, lot of bumps. It will be even worse than the kind of the road we are having. Right? So we use the phenomena of peak forces, water forces, and the cantilevers, and we can map the surface morphology as well. And at the same time, we can count how much is the force between these two substances. That is all can be done. And this is all happening. Those technologies are all already here. Okay. Nowadays, this one more thing has come up. This is a fun interferometer. When you think of some laser passing through a lens, split it into something, here is some external edge created and then up here. So beam coming from here and beam coming from here, they are interfering, give some pattern. And one can find the phase difference. The students must be knowing when we write the property of the wave, right? So wave is some amplitude times e to the power I theta, right? So that theta, that is the phase of the system. So one can understand, find the phase of the system. How one wave is traveling and how much phase difference the another wave is having. One can really find using some sort of interferometer. And these phases are nowadays being used as a new fundamental quantity. Like mass, time, momentum. People have started using phase as a quantity and they are harnessing them for multiple applications. Okay. And here there is another fascinating thing that is again happening. Still to be developed more. You find it. So you see this is a cavity. So once the laser is coming, passing through this, passing, laser light can pass through its, and then once it is there, it can keep on reflecting. So for any laser action, we need a cavity, and then once there is sufficient intensity, then it comes out, and that gives you the laser. Now you see this part of this wall of the cavity, this is with exceeding. So one can harness how much pressure this laser light is putting onto this beam, and we can understand this. Can you imagine that whatever the radiation is falling onto us, it exerts some pressure on us? This thing usually we never think of, but this is true. We are a very heavy object, we don't feel it in our all microscopic world, but when you go to really atomic world and microscopic world, these things do happen, right? One can really measure the pressure exerted by the radiation. Okay, here is another example that one can control even the vibration of the cantilever. And now can you see this dimension is 60 micron. This much thickness this is the thickness of your hair. Within that, see, this is even smaller than that also. And one can really look at the vibration of this. So all these research people are working. This another stuff comes up. So I'm giving you through the different applications of the science that's happening. This device is called the discrete magnetometer. So you see the magnets that we use in speaker's magnet, the round color magnet. This is typically 100 Oersted field. 100 Oersted field. And if you look at the Earth's magnetic field, that if you hang a bar magnet, it will be always in a north-south direction. So how much is the Earth's field? It varies from 0.25 Oersted to 0.75 Oersted. So like here it may be 0.33 in India. So this is a very tiny magnetic field. Magnetic field can be even smaller than this. Right? So their new magnetometers are based on the principle of this quantum interference, which is called superconducting quantum interference device. Based on that, one can sense a very, very tiny small field of 10 raised to power minus 15 Tesla. This much small field can be tested. And yes, these equipments are up there. And as I said, the magnetic field. In order to see the magnetic field, we have a bulk of the material and we sense it. And we say this is magnetized or not magnetized. And this, to understand the magnetic field, we saw this coming from the spins of the electron. So whether we can detect a single spin of the electron, there are a lot more challenges. Those sort of the detections are also important, and you see this magnetic force microscopy, one can see that. So these things are happening. So I am telling you the current challenges also, current development, in what direction all scientists all over the world are working on. This is another interesting stuff to tell you. Optical tweezer. Tweezer we know, right? We use for multiple purposes. So whether we can hold some substance using a light, it looks very fascinating and impossible. If you have a light beam in your hand, laser beam, whether you can pick something. So these are the concept called optical tweezer. You can pick up micron size objects, some cells one can pick up, some bacteria one can pick up using optical tweezer. So that is another thing happening in the science. Few of things are already here at our IIT Mandi in some sense. So we teach our students. Another thing that came up I wanted to tell you about is within the metrology part. Okay. So how small distance one can measure. I told you the thickness of our hair. One can measure it with the 1 year caliper. Right? the micrometer, 1 kilometer. So in few years ago, in 16 that came up, and there's a whole group of the scientists all over the world, and they are working on this quantum metrology, the LIGO detector. Laser interferometer, gravitational wave observer. Another fascinating thing, gravitational wave. Right? So these concepts are very fascinating. What do we mean by wave? Wave that we understand. We put a stone in the water, you will see a lot of ripples, they are going outward. That's it. That's the wave we see. Einstein gave this concept that our whole universe is sitting in a space-time fabric. So there are three dimensions of space, X, Y, and Z. Another dimension is time. On that, one thing, so our whole universe is in that fabric, space and time. When we put our sun somewhere, someplace, like if you stretch a cloth, put a heavy object in this cloth will pull it out. So whatever the other objects nearby this bigger object, they will feel the force of this bigger object. So that's the gravity that he said. Now we can think of, if some event is happening, suddenly that star is blasted off, nebula explosion is happening. So once that explosion is happening, then there will be ripple on your cloth. So those are the gravitational waves. Those were people discussed at the time of Einstein, but recently they were discovered. Right? And once there are the waves coming up, then whether we can understand that the wave exists, and if the wave is happening, then some part will stretch, some part will contract. Using those principles, the scientists have found, yes, there was a gravitational wave, and they can detect up to the sensitivity of 10 power minus 19 meter. So this thing is really unfathomable, but 10 power 19 minus 19 meter. Size of the nucleus is 10 power minus 15 meter. So even a change smaller than that can be estimated with some different ways. And these are the examples, how this is done. A lot of optics. And this is set up for the laboratory. So there is one in the center. One part is Livingston, Louisiana, another part in Hanford, Washington. And these are 7 kilometers long. So these are the two different laboratories. One is in Livingston, Louisiana, another is Hanford, Washington. The one observatory, this is 7 kilometers long, this is 7 kilometers long. So light is passing in this. And they look at the interferometry of those light to find it. Very challenging projects, and groups in India are also part of this project. And these are some real word picture of interferometer. So let me talk about another thing that's second generation I'm talking, quantum entanglement. So two particles are entangled. Once we get married to somebody, so we are entangled. Our life are same. Right? In so here is the technique about what is not entanglement. In quantum mechanics, let me go. So look at this. We take the two electrons in hydrogen atom. So hydrogen atom has one electron, another hydrogen atom has another electron. What are the different possibilities? This electron can be here, this electron can be here. Or this electron can also be here, or this is also here, or this can be here, this can be here. So there are multiple possibilities. That on this, either there is a no, 0, 0. There can be 0 in one, no electron, another one electron, or other electron is here, other there. There are multiple possibilities. There are 4 different possibilities for this situation. We do not know in what state the system would be, where the electron would be. In quantum mechanics, in order to represent this type of the state, they we write it there, only this mathematics. This one state, it may have some chances, another state, it can also have some chances. This is we call the amplitude. Consider this also something. So quantum mechanically all these four states are possible, but some with more probability, some with less probability. So now there is a mixed up state. So they are now these things, all these four states have the shared identity. This is a concept in the quantum mechanics done in 1925. But when we say entangled, so entangled when we say those two states of the electron that you see, right, they cannot be separated. They are now forming as a one single state. Here they are all separated. One can find either this or this or that. Here these two states are entangled. We cannot say what is what. If we determine one, automatically the second one will be determined. So these two things are entangled. So now consider an example that I take two entangled particles with me, and they are now entangled, and one particle I have sent it to Japan. This one is I am having, but this particular is still entangled. And now I do some measurement on my particle, and I find, okay, this is the result. Then suddenly, even without knowing what result has come up here, when somebody measures in the Japan, the result in the Japan will come out to be exactly. If this particle has come out to be in up state, then somebody in the Japan measuring the second particle, though he does not know what has happened in the India, they will determine that another particle will be in the down state. So those two are the entangles. These two are entangled particles that we talk about. But this is very confusing. People were not able to accept it. Even the Einstein has big objection on this. How come somebody in the Japan, they knows that what is done in India? So whether the information is reached to that place, whether information reached to that place faster than the velocity of the light, that was very confusing. So these three guys, Einstein, Podolsky and Rosen, so they gave this idea. So means something else is happening. Maybe we do not know, because this is true, will happen, but why this is happening? So they say there must be some local hidden variable, which right now we do not know, that is taking information to that place. So this was the EPR paradox we talk about. This was done in 1935. Quantum mechanics came in 1935. So Einstein was having one big question on this particular entanglement element. But in 1960, this person, Bell, John Stewart Bell, he was a theoretician in theoretician in particle physics. He thought about it, and he gave his theory, and he said that if this inequality is proven, the relationship of that is proven, then the quantum mechanics is right. Whatever entanglement is happening is right. So this inequality, he gave the theoretical anxiety. And later on it was found, yes, it works that way. So, like here he gave this theory, this idea, that if you have a quantum mechanics, the system, the correlation between those particles should behave like this, if they are at an angle, or if there is a hidden variable theory, it should go like this. And it was found that for this point, both the theories are matching, but at these points, theories are not matching. So this inequality is violated. This inequality is not valid. It's a bit difficult concept, but with this they said, yes, entanglement is happening, quantum mechanics is correct. Whatever the challenges they were saying, this is not the real thing. There is no local hidden variable in the system, but there is a quantum mechanics happening. Okay. Again, this is theory, and here you will see teleportation photo. these three guys. They gave the title name is teleportation. So teleportation sense, these three guys, they got the Nobel Prize in 2022. Dellinger, Crosser and aspects. So they looked at the photons. So they were working in the Europe and Austria. They did the experiment. So they two entangled photons. They took it. One photon in Germany, another in Austria, and they found those photons are entangled. Those photons are really entangled. And after that, many other scientists have proven this entanglement. Now imagine, you have done this entanglement. By knowing the state of this, you have got the state of another one. Or similarly, one can go for this teleportation system. So let me put this one word here. The teleportation of the information is possible. Teleportation of the mass is not possible. When we talk about this entanglement, these are the photons, which are massless particles. When you think of some object, I am made of billions of the cells, right? Cells are made of billions of the atoms. There are so many particles. They are having mass. So you cannot transport mass one place to another place, but information one can still do it in the form of the one can do. So yes, these experiments was done in 97. They got the Nobel Prize in 2022, and these things are done. And there's more detail. And these are very interesting things happening in the field. Let me come on to. I have 5-6 more slides. So all over the world, people are working on this system. So this is a ground satellite quantum teleportation. I said the Dellinger aspects in closure group. They did it between Germany and Austria on this days. China has shown this quantum teleportation or sending the information from Earth up to a satellite. Satellites are say 700 to 1,000 kilometers up over the sky. So a lot of work has been done. And China is very much ahead of us. In India also, there are 3 groups working on this. They have shown this entanglement or this quantum teleportation up to a distance of few kilometers. 2 kilometers they have shown it, or few hundred of meters they have shown it. Okay. So this is the photographs. That's today 14,000 kilometers. They have sent a signal from here to the satellite, quantum signal from here to the satellite, and then they receive. And quantum signals are the most secure signals. Very important. Quantum communication, teleportation, cryptography, all based on these principles. So if a country is very good in this, they can break all those codes. So yes, that's very challenging, and people are doing it. And now you come to the little bit of the computer and some photographs. More slides. So we have a quantum computer that we talk about, and we say this will perform some calculation. Right? It is based on the fundamental principle of quantum mechanics. And the calculation done by this computer would be much, much faster. Suppose you have to break a code. So I have some password on my computer. You want to write a code to crack this. Then you will look at all the possible password I can. I say I have a password of the up to a 4 decimal digit. Then in 10,000 different trials, you will certainly hit my password. If I add more complexity, it will be more difficult to do it. So that's why every time you see that you choose your password, put some capital letter, put some alphabet, and also put some digit or some symbol. So to make it more complicated and more difficult for the computer to crack. But this all can be cracked in due time. If you have a quantum computer, if you know there is a 10 digit of the things, those things can be done much faster. Password can be broken in much faster. So that's a possibility that we talk about. But so far nobody has done this. And to show that they are very fascinating, so in 1982, this very, I think he is the second most famous physicist after Einstein, Richard Feynman. He proposed that we can create the machine based on the fundamental laws of quantum mechanics. Very first time he said, in 1982. Computers were there, but based on fundamental law of the computer. So in what those computers can do, this person, David Hughes, that he developed a quantum Turing machine and he made this quantum circuit for those computers. This guy Peter Szor, but now these are happening in not far away times, 85 and 94. Right? So Peter Szor came up with the algorithm that how one can factorize a very large number. Whenever you see that some quantum computer, somebody has made it, and they have shown the quantum supremacy, they show only this factorization of a prime number using this technique. And how fast it can do compared to the classical computer, you could say now my quantum computer have a supremacy over the classical computer. And I just want to add one more person's name here. This is Indian person, Love Grover. He developed a new quantum search algorithm with a certain complexity. Right? Suppose you have a dictionary, you have to choose some word and number. You have to look one by one. Consider if the dictionary you have a word given, and you go to the alphabet A, then to the next alphabet, slowly you choose it because they are arranged in a particular order. If something is not arranged in a particular order, then you have to look at each and every word to find a particular desired word. That's in the search. But he gave an algorithm in a computer that you can find that particular word using square root of n times of iterations. One can get it. So this is our Indian American. So I have, I think, almost last slide. I'm showing you. So a lot of things are happening in quantum computer. We see this sort of the photographs. So whenever you see in the newspaper or in any magazine quantum computer, we see a computer like this. Yeah. This is not a small computer like this. Let me add one more. Even if you make a quantum computer, we will not be carrying it like our laptop or this, and it may not be useful for our daily purposes. But there are some problems which our classical computer cannot solve it. Quantum computer can do that more effectively. For doing 2 plus 2 equal to 4, for this computer is more difficult than our calculator. Next, keep this thing in mind. But some different tasks which cannot be, I will show you some tasks what you can do. So we see this sort of the stuff, or this sort of the stuff almost. So this is IBM computer, this is a Google computer. Whatever this machine sees, you are seeing it, is a dilution refrigerator. We have a refrigerator in our home, which works, the freezer temperature in the freezer is minus 20 degrees centigrade. But when you think of quantum computer, this temperature is in a millikelvin. This is not 1 Kelvin. 1 Kelvin is minus 272 degrees centigrade. Minus 272 degrees centigrade is 1 Kelvin. And this is in a millikelvin. This works in the millikelvin because quantum mechanics, quantum phenomena can be realized at a very low temperature in order to reduce the noise. So in the fridge there would be some place at the bottom where you are putting a processor, quantum processor, that is doing all the calculation. All that you see blinking. And these are the chips. This goes and somewhere they chip on one of the plate here. And there are some electrical circuits. And the electrical circuits for those things passes through hollow tube. And these are some quantum computer, the DRAM quantum computer. There is some optical quantum computers come up. Some people are working on ion-trapped quantum computer. So with this I will end. There are a lot of advantages in this drug discovery, material science, cryptography, initial modeling. You can do that. But there are many challenges. These things are very expensive quantum computer nowadays, whatever is existing one is coming in the 100 crore. So there are many challenges, but there are advantages. So with this, I end my presentation. Thank you very much. If you have a question, maybe after the talk you can ask. Yeah.
Thank you so much, sir. Thank you for the